Hello, everyone. Thank you for staying and listening to my presentation. So I'm Mersabel Veciana from the Advanced Water Management Center from the University of Queensland. I am currently taking up my PhD. So I'm here to present our study regarding the electrochemical oxidation of PFAS in water using BDD and the role of sulfate radicals in the treatment as well as adsorption in the treatment system. So just a background, this study is still an ongoing project, and it is part of a project which is composed of two stages. So the first stage is focused on up concentrating PFAS in wastewater. And then the next stage, which is my study, is focused on the destruction of PFAS in wastewater with the use of electrochemical oxidation. So I think Suzanne in the previous session discussed some of the theories with the electrochemical oxidation. So EO is a treatment process which uses electricity to produce oxidative species such as hydroxyl radicals in the anode. So you can either have a direct oxidation. It is where your pollutant is directly oxidized in the anode surface, or you can have an indirect oxidation where your pollutant, which is in the bulk solution, is oxidized by the oxidative species being produced, such as the hydroxyl radicals. So recently, studies have shown that sulfate radicals can also be electrochemically produced from sulfate ions that are present in water. So this is a viable option because sulfate radicals have high oxidation potential, which is comparable to hydroxyl radicals. It has a wider range of pH which you can apply and still have an efficient treatment. And it has a higher half-life than hydroxyl radicals. At the same time, sulfate ions are already present in wastewater. So this reduces the need to add additional chemicals in actual wastewater treatment applications. So EO, or electrochemical oxidation, have been studied, and there is a lot of researches about it regarding PFAS degradation. Several pathways have been proposed, but all of them, or majority of them, agree that for PFAS degradation to initiate, it needs the PFAS compound to be directly oxidized first at the anode surface, and then it produces this these PFAS radicals. And then after that, it goes into the different degradation pathways until complete mineralization. However, for the recent application of sulfate radicals, so far the studies that are only available for sulfate radical application for PFAS degradation are mainly focused on PFOA and HFPODA. So they propose that aside from the pathway where the PFAS degradation is initiated with the direct oxidation in the anode surface, they also propose that sulfate radicals are able to initiate PFOA degradation by indirect oxidation. So my study is focused on investigating how the presence of sulfate radicals affect PFAS degradation. Mainly, for me to do that, what I did was compare treatment efficiency between two electrolytes. The first one is sodium nitrate, and then the second one is sodium sulfate, which serves as a source for the sulfate ions for sulfate radicals production. So this is a schematic diagram of my reactor. So mainly I investigated 10 PFAS, which is composed of 7 PFCAs from C4 to C10, and then 3 PFSAs from C4, which includes C4, C6, and C8. So these PFAS are treated individually with an initial concentration of 1 ppm. And it is treated for 6 hours using EO with an constant current of 20 milliamps per centimeter squared. And then we did a parallel run, or we call the blank run, at pH 2. So this was done similar to the EO, except that there's no electricity. So we did this to see how much of the PFAS is being absorbed in the system. And this time we adjusted the pH of the solution at 2 because during the EO treatment, we observed that the pH of the solution decreased to 2 or less within 15 to 30 minutes of the treatment. So since PFAS sorption is pH dependent, we decided to adjust the pH solution for our blank runs. And then we took some samples at designated time intervals, and then we analyzed it for PFAS and for fluoride. However, my fluoride results are not yet available, so my presentation will focus on my PFAS results. So this is just a photo of my setup. And then, so comparing the PFAS removals between the sodium nitrate, which is represented by the red bar, versus the sodium sulfate, which is represented by the blue bar, we saw an increase in the PFAS removals with the presence of the sulfate radicals. The PFAS removals that we got range from 5% to greater than 99% for the PFDA. Also, we can see here that we can see higher PFAS removals, higher increase in PFAS removals with the presence of the sulfate radicals for the shorter chain PFCAs, which are C4 to C6, as compared to the C8 to C10 or the longer chains. We were able to observe greater than 30% increase for the shorter chain PFCAs with the presence of sulfate radicals. However, for the longer chains, we only observe around 2% or lower increase. On the other hand, for the PFSAs, we observe also an increase in the PFAS removals with the presence of the sulfate radicals. And you can see here that for the long chain PFSAs, particularly C6 and C8, they have a higher increase in removals with the presence of sulfate radicals if you compare it with the longer chain PFCAs. In terms of the intermediates, so we also measured the intermediates during the treatment within the 6 hours treatment. For the PFCAs, we observed that shorter chain PFCAs are being produced during the treatment, and the presence of the sulfate radicals increase the production of the shorter chain PFCA intermediates. However, for the PFSAs, for example, here for the PFAS, we did not really observe any production of short chain PFAS, either for the sodium nitrate and the sodium sulfate electrolytes. On the other hand, for the kinetic rates, we observed that majority of the PFAS increase in kinetic rates with the presence of the sulfate radicals, except for PFDA. And then comparison of the energy consumption, we observe a decrease in the energy consumption with the presence of the sulfate radicals. Particularly, we observe that there is a big decrease in energy consumption in the shorter chain PFAS, again for the C4C6 here for the PFDAs, and then for PFBs here. However, we observe a slight increase in the energy consumption for PFHPA and for PFDA. So we also investigated how much of the PFAS is being absorbed in our system, just to see whether we are really degrading the PFAS through EO, or our majority of the PFAS are just being absorbed in our system. So we did blank runs for some of the PFAS at 2 pH, mainly pH 5, which is represented by the blue data, and then at pH 2, which is represented by the red data. Here you can see for the short chain PFAS, specifically for PFBS, the decrease in the concentration for the 2 pH conditions for the blank runs were not really that much. So it's still less than 10%. However, if you increase, however, for the longer chain PFAS, we are seeing an increase in the adsorption at pH 2. For example, here for the PFOA, we have around 70% PFAS loss due to adsorption at pH 2. As compared here for the pH 5, there's really within the 10, it's the PFAS concentration here are still within 10%. On the other hand, for PFDA, the PFAS loss further increased to 99% at pH 2, which if you remember, PFAS removals for PFDA was also at 99%. So at that point, we really cannot tell whether the removals we observed during the EO for the PFDA was really due to electrochemical oxidation, or whether it's just absorbed.
3 minutes remaining.
Okay. So this is just, again, the summary of the PFAS removals, but this time with the adsorption results, or with the PFAS losses due to adsorption, which is now represented by the yellow bars. So overall, you can see that even though there are PFAS sorption in the system, the PFAS removals with the EO treatment are still higher compared to the PFAS losses due to sorption. At the same time, you can see that for those PFAS which have lower sorption, or where a lot of PFAS remain in the bulk solution, those are the PFAS compounds where we see higher enhancement with the presence of sulfate radicals. The same can be said for the long chain PFSAs, which are, in general, the PFSAs adsorb less compared to the PFCAs. So based on these results, we are seeing that overall the presence of the sulfate radicals is improving treatment efficiencies for EO, and the results suggest that the presence of the sulfate radicals enhances indirect oxidation. However, we still cannot really finally conclude in terms of the mineralization because we're still waiting for the fluoride results. In addition, we would like to emphasize that PFAS sorption, particularly at the corrected pH of the operating system, needs to be accounted just to avoid possible overestimation of reported treatment efficiencies. So lastly, I would just like to acknowledge that this project is partially funded by the Australian government through the Australian Research Council, and would like to acknowledge our industry partners, as well as my supervisors and the rest of the team, which are mentioned at my first slide. That's it. Thank you.